So these are your 11.3, 11.4 video notes. This is the third day of conics on hyperbolas. Hyperbolas are created by cutting the two cones of the plane that runs perpendicular to the bases, and creates actually two pieces. So a hyperbola has two parts to its graph compared to the other days of conics. Hyperbola has some good applications. They're a little more advanced than what we can do with our basic equations, so we won't be doing word problems for hyperbolas, but we'll definitely do the equation writing and the graphing aspect of it. So let's kind of get going on that. There are some things we can just talk about quickly, like orbital patterns. So elliptical, we said we know that's a typical planetary orbit, but you can also have things that will come into your solar system and leave, and that could be parabolic or hyperbolic. And those things would be like comets would be a classic example of that. Some structural design ideas. The cooling towers in a nuclear power plant are actually a hyperbolic solid. So right along the edge here, you can see these curves being similar. Those are actually two halves of a hyperbola. Now it kind of gets cut short up here because of the tower design. But how this works is cool air will come into these vents at the bottom, and it will cool water, which is stored in pipes in here. And that water will then cool the reactor. Cool air in, hot air out. Cool air in, hot air out. So that's a design for cooling nuclear reactors. Sonar mapping is a pretty classic application of hyperbolas. It's been around forever. Basically what happens is you've got a transducer off the back of your boat. It looks like a little hockey puck. It doesn't really emit from the bottom. It's usually attached to the back, right? If it's in a bigger ship like this, you'd probably pull a sonar array. So you'd have multiple monster pucks being dragged on cable, and you can get all kinds of readings and stuff like that. But anyway, from a simple depth finder in my fishing boat concept, the signal gets bounced off the bottom of the lake, and then it comes back up, bounces off, come back, and it does that nonstop. While the boat's moving, what it's going to do is it's going to contour the bottom. You can see this if you're looking kind of carefully how this is moving across. This image is a depth finder. And you can also see the fish, right? As that fish goes through, that sonar signal will hit the fish and bounce back, hit the fish and bounce back. So your depth finder doesn't just do depth, it also marks fish, which is a good use for fishermen. So how is this connected to a hyperbola? Well, the two halves of the signal going down and coming back up are actually two halves of a hyperbola, turns out. So it's a hyperbolic signal bouncing up and down off the bottom of the lake, reads depth, and also picks up images of objects. A similar technology would be topography mapping. So that'd be the mapping the contour of the Earth, and you'd have basically on the bottom of a plane a monster sonar or monster puck, you want to call it that, and it would send a signal down to the Earth and bounce it up and down back to the plane, and it would contour map the Earth. So a topography idea. Technology has been around for a long time, and pretty good application of a hyperbolic signal. So let's start talking about some design ideas. So every day we kind of have this geometric definition, like some kind of relationship that we can use for an application. This one has an application. We're just not going to do it because, again, it gets to be a little bit more complicated problem. But the connection here, or what's the special, unique thing about hyperbola, is that these two distances from focus to a point on the graph, from that same point to the other focus, if you subtract those two links, you get the distance between vertices. And that does have an application. Now, we're not going to do any word problems with hyperbolas, so we're going to get into our graphing and equation writing next. A little bit of design idea here. So there's only really one consistency between ellipses and hyperbolas, and that's the distance from the center to the vertex is called our A distance. Otherwise, just about everything else is different. The equations have kind of a similar look. That's about it. There is no such thing as a major axis with a hyperbola. So the A value is center to vertex, but isn't necessarily bigger. Like in an ellipse, it would be the bigger number. We also have to create some kind of structure to draw our hyperbolas because they don't have like a focal diameter concept like a parabola would be. So we're going to create some asymptotes. And once those asymptotes are created, that'll give us the shape of the two halves of the hyperbola. And we'll talk about how to create those in a second. The B distance, which there is a B distance, is actually from center to here. We don't really plot a point because it's not something that's part of the graph, but it'll probably be more like a marking, and I'll show you guys that in a minute. The central box doesn't have to be drawn because the asymptotes would do the job, but I kind of like the central box as my guide because when I go to draw asymptotes, it's an y equals mx plus b concept, and whatever the slope is, I mean, I can count it, and then I can reverse and count it, but it's actually much easier just to go corner to corner through the central box. So I like the central box for the purpose of sketching my asymptotes quickly. You don't have to have it, but it's helpful. Okay, let's break down the equations. So, we've got two types. I'll kind of flash back and forth here. We've got left-right opening and up-down opening, or we would call this a horizontal. We would call this vertical. If you look at your equations, the main difference is x squared minus y squared and y squared minus x squared. That's how we'll tell left-right or horizontal or vertical. It's not about A or B, especially not about A. A is not necessarily bigger in a hyperbola. So that's true in an ellipse. It's not true in hyperbola. What is true in the equation is A squared, B squared are always set in place. So it'll always be A squared, then B squared. What's going to change is which way this will go. And how I know which one I have is if it's x first, or x squared minus y squared, that's horizontal. If it's y squared minus x squared, or y is first, y being vertical, y squared minus x squared, then it's vertical. Simple way to keep track of that. And then your asymptotes, you've got equations that are just mx, in this case no b because we're going through the origin. But how do I know if it's b over a or a over b? I don't memorize that fact. What I do is think about the a distance being to the vertex, and then the other distance is my b. So for example, this would be up b over a. Now just me understanding the distance from center to vertex would tell me what this is without me having to memorize which one's which. We got a foci equation also, a c squared equation, but now this is plus. So actually when it's like hyperbola, subtraction is the equation, plus is the c squared equation. So that's kind of how I keep that straight too. And that'll help us calculate the distance c. C is still from center to foci like it is in an ellipse. So there's one more connection we can make. But a reminder again, a is not necessarily the larger number. There is no such thing as a major axis. The words that'll be used will be transverse axis, and what transverse means is that's the way the two pieces of hyperbola open. They open left, right, or they transverse the horizontal axis, or they transverse the vertical axis. Okay, let's get into some graphing and check it out. Of course, shifts, right? So shifting again doesn't do anything special for our work. It'll move our center of our central box away from the origin to somewhere else. Fine, no big deal. X minus h, y minus k. I've done that a million times, right? And then when we go to write our asymptotes, what we'll do is we'll put that new center into the equation of the asymptote, which will create a point slope look. But it's really easy to do because once you have gotten the basic equation, if we're doing the problem kind of like I've done this, and all I got to do is drop in y minus k and x minus h and create that. So pretty easy to work with. Okay, let's get it going. So right away, the first thing I would identify is this is horizontal because x squared minus y squared. X is first, or x over a, however you want to talk about it. So it's horizontal. A happens to be the bigger number here, but it doesn't mean it's the major axis. There is no concept of like a major axis. But this is a squared and b squared set in place. So a is 3, b is 2, c is a calculation using the c squared equation. And then vertices. Now, knowing that's horizontal, I would know that they would sit on the x-axis, so I don't need to see the graph to understand this. And same thing with the foci. Asymptotes. Now, how do I know it's 2/3 again? Let's do this. Let's pop up the graph and show you. So when I go do my, sorry, there's an asymptote. We'll come back to that in a second. But doing my A and my A and my B and my B are just kind of marked, so I'm counting 2 and 2, and I make my central box. It shows up. There we go. Then I go asymptote corner to corner, which is why I like the central box. You know, again, you don't need to. You could just run slope. But how do I know it's 2/3 and not 3/2? Well, if this is the A distance, then my up distance is B. Up B over A. That's how I get my 2/3. So pretty easy. And then I got to go sketch. And so draw your graph. Run it along the asymptotes, left, right, opening, hit your vertice on both sides. And there you go. So there's a little bit of structure you got to do up front before you draw the graph, where the other 2 days we could just kind of get our information and go. But no big deal here, right? And then you put your little arrows on the end and you got it. So if we go to shifted, shifted again doesn't affect a whole lot. You're going to have a new location besides 0, 0 to operate from, which is a new center. I'm just going to pop up all the info here quick. So our center at -5, 8. So let me count that. So we're up here, and we'll draw this to talk about in a second. One thing I highlighted here, and this with you guys in the ellipse notes too, is that when I look at this coordinate -5, 8, what should be in the same visual horizontal line would be the center, the vertices, the foci. So that means they all have the same y value. So they all have the same value, y value of 8. And then what I can do, again, I don't need this image to figure these things out. I can just start at -5 and I can count the a distance. So -5 minus 3, -5 plus 3 using the a. And then -5 plus the c distance, -5 minus the c distance will give me my foci. And then asymptotes, again, if I've got this equation, all I got to do then is drop in y minus k, my slope, x minus h. And again, sketching, right? So go ahead and draw a graph. So shifting shouldn't affect much at all. And do a little rough sketch here. Just doing something from a different location. Okay, let's see one more graph, then we'll go equation writing for a few minutes. So like an ellipse equation, this has to read equals 1, so you have to do a little bit of work up front. You notice here that actually the a squared, b squared are the same. If this was an ellipse equation, that would be a circle. All this means for us is that we've got a square as a central box, and our slope is 1. Because if we're doing our a over b or b over a, it's going to be 2 over 2. And then a c squared calculation, a c calculation. Again, vertices, now knowing that this is vertical, and the reason I know that, oops, sorry, 1 second here, let's fix it. So y squared minus x squared, I had to fix that quick little glitch there. So anyway, vertices then, because this is an up-down opening, or vertical, that means that my vertices and my foci would sit on the y-axis. That's how I know I have these as my coordinates. And then asymptote. Now, in this case, they're the same numbers, so is it b over a over b? Well, if it's vertical, then center to vertex would be my a distance, so that would be up a over b. So this is an a over b slope. And then going ahead and sketching my graph, right? So again, I would do my 2 and 2. So there's my actual vertices, my central box, asymptotes corner to corner, and then do a sketch. You know, all 3 days of graphing, I think graphing is probably the easier of the two concepts. I think it's the equation writing where there's maybe a little bit more to think about, but whoops, okay, got a little carried away on that one. Let's try that again. Anyway, sketching, no big deal. And then we go do our shift. You know, again, all it's going to do is move us away from 0, 0. Again, nothing too special there. So, but we do have to read equals 1, so we got to do that. Then grab our new center, and then this time, because everything is in the same visual vertical line, that means all the x values would be the same. So if I do a center at 7, 5, you can see that all of them sit in the same vertical line, which means the x value 7 is the same. And then to get these, again, I don't need to see the graph to do this. I can actually do this by counting. So if my a distance is 2, 5 plus 2, 5 minus 2. 5 plus c distance, 5 minus c distance to get to my foci. And then asymptote, just drop in the center, so y minus k, x minus h, and you got your asymptotes. And then sketch your graph. So again, sketching pretty easy to do. Now as we move into equation writing, you're going to kind of notice a bit of a theme going on probably from that kind of corresponds to ellipses a little bit and how we attack stuff. But otherwise, you know, using our different equation, of course. Okay, let's do equation writing. So like always, you know, the first thing I want to do is sort of figure out what I've got going on in terms of visualness. So that means I've got to, let's get it clicked in here. So there we go. So I know what my a distance is. It's 2, I can count that. I got my c, which is 3, that's my foci. You know, that's kind of obvious right there. I can go ahead and calculate my b squared, and then which equation I have be based on what I visualize. So that's got to be a left-right opening based on, or horizontal based on what I see there. And then, you know, just go ahead and drop in your stuff. So I got my a, got my b squared, drop them in. Done. Now here you notice that the a squared is actually smaller. So again, there's no such thing as a major axis with a hyperbola. So kind of a similar approach to ellipse. So again, what do I know when I look at this? Well, I got an a and a b. Now here's the thing, the a clearly is 3, center to vertex. Am I sure this is 1? Am I like confident of that? How would I know? How would I verify it? And the way you can verify it is right here. If you got a slope of 3 over 1 or a slope of 3, then b has got to be 1. So now I know for sure that's what's going on. And I can go through and say that's a vertical. Let's go ahead and drop in our numbers and we're good. So there's a squared being 1. Remember, always a squared then b squared. So equation writing in this case so far probably seems kind of simple because I pretty much have everything I need right off the bat. Our last one, let's just gather some information here. What's our center? What's the a value? Center to vertex, I can count that. I do know it's horizontal. It's shifted because my center is, you know, not at 0, 0. So x minus h squared, y minus k squared. Remember, a squared, b squared always set in place, but x squared minus y squared is horizontal. And then I need one more piece of information. It's like, what is the b value? I don't have a c value. I don't know what my b value is. I can't assume any kind of central box or asymptote thing here. So what I'm going to do is grab a coordinate. Could have grabbed this one, but I'm going to grab this one because easier to work with. Now, if you look at a, x, y, h, k, there's 5 variables. There are 6 here. I know 5. Well, if you know 5 of the 6, you can go solve for the 6th. So we'll just run through and plop our numbers in. So this is x minus h, y minus k, and then a little bit of solving for b squared. Remember, you only got to go as far as b squared. You don't need to go down to b because the equation only requires b squared. And then I would drop it in. Now, again, I don't like this look, so I'm going to flip and multiply here, get rid of that, and have it look a little bit cleaner. There's my final equation. All right, and that's your notes for hyperbolas, graphing, equation writing.